In physics and engineering, our entire job is pretty much describing how things exist and move around in space. And to do that, you absolutely need a map, a really precise way to define every single point. So today, we're going to dive into the most essential tool for that job, coordinate systems.
Okay, so to really get why these maps are so crucial, let's start with something I think we've all felt when staring down a really complex problem.
You know that feeling, right? You're just wrestling with an equation, the algebra is getting super messy, and you just feel stuck. It's like you're trying to hammer a square peg into a round hole, and it's just not working.
Well, here's the thing, and this is so important. Often, the problem isn't that you can't do the math. The problem is that the math is way harder than it needs to be because you're using the wrong framework. You're using the wrong map for the territory. Seriously, choosing the right coordinate system can take a nightmare problem and make it, well, almost easy.
Let's think about coordinate systems like a GPS giving you directions. I mean, there's more than one way to describe how to get somewhere, right? And the best way totally depends on the landscape you're in. Now, we're going to focus on what are called orthogonal systems. That sounds fancy, but all it means is that the directions we measure along, like up, down, left, right, forward, back, are all at right angles to each other. That one simple rule makes them so much easier to work with. It's a real game changer. First up, the one you already know and love, the Cartesian system. You should think of this like a city grid. To find any point, you just go X blocks east, Y blocks north, and Z floors up. It's absolutely perfect for anything with straight lines and square corners. You know, like boxes, rooms, or buildings. Next up, let's look at the cylindrical system. For this one, imagine you're standing at the center of a radar screen. To find a point, you first turn to face a certain direction. That's your angle, phi. Then you walk straight out for a certain distance, that's your radius, rho, and finally, you go up or down to a certain height, that's z. This structure makes it the perfect system for describing anything round, like pipes, cables, pillars, you name it. And now for the spherical system. Think about locating a drone flying around in the sky. You'd start by turning to face its general direction on the ground, that's your horizontal angle, phi. Then you'd tilt your head up to look at it, that's your elevation angle, theta. And finally, you'd measure its straight line distance from you, that's r. This system is the clear winner for anything sphere-shaped, like planets, stars, or even the radiation pattern coming off an antenna. So, we have these three completely different languages for describing a point in space. But how do we translate between them? Well, that's where a few simple rules come into play. Okay, this slide right here is basically your Rosetta Stone for coordinates. Look at the right side. That's how you go from a Cartesian point, x, y, z, into cylindrical. The radius, rho, is just the Pythagorean theorem, super simple. The angle phi is just some basic trigonometry. And the best part? The height, z, stays exactly the same. It's the one thing they have in common. All right, theory is great and all, but let's make this real. We're going to take a point from our Cartesian city grid and find its address in the cylindrical radar sweep. Let's do it. So here's our problem, and this is straight from the source material. We've got a point P, and its address is x equals -2, y equals 6, and z equals 3. Our mission, find its rho, phi, and z coordinates. Okay, let's just go step by step. First up, we're going to find that radial distance, rho. We just plug our x and y values into the formula from our Rosetta Stone. So the square root of -2 squared plus 6 squared, that gives us the square root of 40, which comes out to about 6.32. Boom, that's our distance from the center axis. Next up is the angle, phi. We take the inverse tangent of y over x, which in our case is 6 divided by -2. Punch that into a calculator, and you get 108.43 degrees. And here's a really important sanity check. Since our x is negative and our y is positive, we know the point has to be in the second quadrant. And guess what? Our angle puts it right there. Perfect. And we're done. The height, z, doesn't change. It's still 3. So our final coordinates are a radius of 6.32, an angle of 108.43 degrees, and a height of 3. It's the exact same point, we're just describing it in a different language. See how that works? Pretty cool. But hold on. You've got to be careful. Transforming the coordinates of a point is one thing. But what if you need to transform a vector? Something that has both a size and a direction. Well, that is a completely different ballgame. So here's the trap you need to avoid. A location is just a spot, right? A vector. On the other hand, describes a direction at that spot. To transform a point's location, you use those simple formulas we just practiced. But to transform a vector's components, you need a much more powerful tool, a transformation matrix.
And why is that? Because in cylindrical and spherical systems, the directions of the axes themselves, like outward or sideways, actually change depending on where you are. This is a huge distinction that trips up a ton of people. All right, let's wrap this all up and put these awesome tools right into your hands.
So here's your 3-step guide. First, always match your coordinate system to the geometry of the problem. If it looks like a box, use Cartesian. If it looks like a cylinder, use cylindrical. Second, know what you're actually transforming. Is it just a location or is it a direction? You gotta pick the right rulebook for the job. And finally, just follow the formulas. If you do that, you can confidently translate any point or vector between these systems without breaking a sweat.
So there you have it. You now have a universal GPS for describing the physics of our world. This is the fundamental language for everything, from designing a new antenna to mapping a gravitational field. The only question left is, what are you going to build with it?